Swayam Prabha. Digital India. Educated India.
Hello and welcome to today's class. So, last week we shifted our attention to building cryptography, and that is what we will continue with for the next few lectures. So, in particular we will start with hardness assumptions, and we will study the following number theoretic assumptions: factoring, RSA, discrete log, and computational and decision Diffie-Hellman. All of these are going to succumb to quantum attacks, as we will see later, but first we will study these assumptions and we will try to understand how to build cryptography from them. So, in particular what we will study is how to construct one-way functions, one-way permutations, trapdoor permutations. We will study a key exchange protocol and symmetric key encryption, and then we will subsequently build public key encryption. Alright. So, let us get started with assumptions. So, let us begin with the most famous assumption that was broken by quantum. So, this is the factoring assumption. Okay, and in order to define this formally, we are going to have to define a particular algorithm which will generate the the instance of the hard problem for us. So, I am going to call this as the gen modulus algorithm. Okay, so, let gen modulus be a polytime algorithm which on input 1 to the n. So, here 1 to the n is basically the unary representation of n. Okay. And we will see why this is important. Okay. So, basically I want the algorithm to run in time polynomial of n. So, I want my parameter to be n. If I represent this n in binary, the size will become log n. Okay. So, that is why I am representing it in unary. Alright. So, this is n in unary representation, and this algorithm is going to take this number n, and what it does is it outputs n, p and q, where n is equal to p times q. P and q are n bit primes except with probability negligible in n. Okay, so, this is the role of the gen modulus algorithm. So, it is a polynomial time algorithm. It will run in time polynomial in small n, and it is going to output some capital N as well as two large prime numbers, n bit prime numbers p and q, such that n is equal to p times q. And essentially, as you can imagine, the idea here is that I want my gen modulus to generate a modulus n, capital N, which is going to be hard to factor. So, that is the goal here. Now, we will consider a factoring experiment, and then we will use that experiment in order to define the factoring assumption. So, we are doing this a little bit formally. Okay, so, consider the factoring experiment. And I am going to parameterize this experiment with the adversary and the gen modulus algorithm. Okay, so, let me just write that separately here. So, I am going to call this experiment as factor, okay, for some adversary A and for some gen modulus algorithm. Okay, and what is this factor experiment going to do? So, it will run gen modulus to get N, P and Q. Okay. Then A is given this modulus N, and it outputs some factors P prime, Q prime, and we define the output of the experiment to be 1 if P prime and Q prime that were output by the adversary are indeed a valid factorization of capital N. So, if capital N is P prime times Q prime, else we define the output to be 0. Okay. So, here recall that A is going to be a probabilistic polynomial time adversary, and this A is asked or given the task of factoring this large composite number N. Okay. So, this is our factor experiment. Is it fine? Okay. So, good. So, this is just the factoring experiment. Now, we will say that factoring is hard. Relative to some particular gen modulus experiment, if for all probabilistic polynomial time algorithms A, there exists a negligible function such that the probability that the experiment outputs a 1 is negligible, right. So, the probability that this factor experiment for this A and this gen modulus, right. So, this is given some 1 to the n, and the probability that this experiment outputs 1 is negligible in n. So, this is very standard crypto parlance. Familiarize yourselves with it. So, what we are saying here is that we define factoring to be hard relative to a given gen modulus if for any PPT algorithm A, the probability that the factoring experiment which we defined in the previous page, the probability that this outputs 1, right, which means that I used gen modulus to generate something, I fed it to the adversary outputted valid factors, right. The probability that all this happened should be negligible in n, right. So, remember that negligible means it is decreasing fast than 1 over super poly. Okay, and the simplest example is 1 over 2 to the n. Okay, so this is what we mean by factoring, and the factoring assumption. So, this is so far we defined the factoring experiment, and we said that when is factoring called hard. Now, the assumption of factoring is that there exists a gen modulus algorithm for which this factoring is hard. Okay, so let me write this. So, the factoring assumption So, this notation is really important because as things become more complicated, it will be really crucial to use sort of the right notation and work it out rigorously. So, the factoring assumption is the assumption that there exists a gen modulus algorithm relative to which factoring is hard.
Okay, so this is a definition. Okay, good. So let's move on to more assumptions. So the second assumption that I want to show you is the RSA assumption. So this is of course a very famous assumption by Rivers, Shamir and Adelman, got them the Turing Prize. So the RSA assumption is related to the factoring assumption, but it's actually a stronger assumption. So if factoring is easy, RSA is definitely easy, but it could be that factoring is hard and RSA is still easy. So in fact, there are some very interesting mathematical attacks on the RSA assumption. There's a very nice survey called 20 years of attacks on RSA. This was itself written maybe 10 years ago, but the ideas are, still very relevant. Okay, so good. So this RSA assumption, what was the reason for introducing it? Well, what we'll see hopefully in today's class, if not today's then tomorrow's, is that the factoring problem gives us a one-way function. So this is already very intuitive based on all the stuff we have said so far, that you can compute the multiplication in the forward direction. It's hard for us to invert, right? It's hard to find the factors. This gives us a one-way function. But it turns out that factoring by itself, we don't know how to use it for something like public key encryption. Because in public key encryption, what you also need is a way to decrypt an encryption, right? And for this, what you need is some notion of a trapdoor. So what the RSA assumption will give us is a trapdoor one-way function. In fact, it will give us a trapdoor one-way permutation. This will ensure that we can, with the help of a trapdoor, we can also go backwards efficiently. We'll define all of this more formally. But this is the reason that we have this RSA assumption. We don't really know how to use factoring in an efficient way to build, encryption schemes. So similar to the treatment of the factoring assumption, let's here consider, Gen RSA algorithm. So this is, as usual, a PPT algorithm, which on input, 1 to the n, outputs once again a modulus n, which is again the product of two primes, large primes p and q. It also outputs two integers e and d, such that GCD of E phi n is equal to 1 and ED is congruent to 1 mod phi n. Okay, so what is this phi n? Let's define everything. So this is known as Euler's totient function. Okay, this is the number of prime, it is the number of numbers, in fact, less than n, which are relatively prime to n. So unfortunately in this class we will not have a lot of time to go into number theory. I encourage you to read more about this offline. But we will of course define everything for completeness. Okay, so this phi of n, this is Euler's totient function. It's defined over here, and yeah, so if the GCD of E and phi n is 1, then it is easy to see that there will exist a D such that E times D is congruent to 1 mod phi n, and this will follow just by the extended Euclid's algorithm if you've seen it. So if the GCD of two numbers is 1, that means that there is a linear combination, let us say A E plus B phi n equals 1, right? and now b phi n mod phi n will become 0, right? So that means that a times e is congruent to 1 mod phi n, okay, and this a is what we will define as d. Okay, so basically, yeah, this is, you know, by extended Euclid's algorithm. There exists, so maybe I'll stick with D here, such that DE plus F phi n is 1. Okay, so therefore, you know, taking mod phi n on both sides, this gives you that E times D is congruent to 1 mod phi n, right? Because this will obviously cancel mod phi n. Okay, so anyway, unfortunately, we will not need to go into all this too much. It's a pity because it's really interesting stuff, but our focus in this course is different. So for now, suffice to say, what's the bottom line? We have this gen RSA, okay. This will give us, you know, n, capital N, which is the product of 2 primes P and Q. It will also give us E and D, such that these conditions hold. Okay, and yeah, phi n, I mean, in case you are wondering what's the relation with this capital N here, basically we'll consider the group Zn star, and phi n will be exactly the order of this group. So you will see where that comes up later. Okay, we will talk about that. So now, having defined a gen RSA algorithm, we will proceed as in the case of factoring to you know, define this RSA problem, right? So we have to define the RSA assumption. So very intuitively, the RSA assumption is going to be that you know, I give you E, I give you N. So remember, here we have N, right? We have E and we have D. So what we will do eventually is that this D is named D not as a coincidence. D here stands for decrypt, E stands for encrypt. So essentially this D is going to be private for us, okay. N and E are going to be public. So basically the RSA experiment is going to say that if I give you capital N and I give you this E and I give you a random Y in Zn star, then can you compute an X such that X to the E is 1, is Y, sorry, since I gave you a Y, right? So compute X to the E which is equal to Y. Okay, this is going to be the question. Let me write it, so then it will be very clear. Okay, so what is the RSA experiment? So once again, you know, this will be with respect to some adversary A and with respect to, you know, some algorithm gen RSA, right? So here once again I am going to run gen RSA 1 to the n to get N, E and D. Okay, now I will choose a uniform Y Z capital N. So not good to be sloppy about case here because they mean two different things. So choose a uniform Y in Zn star, and now A is given, you know, N, E and Y, and outputs X in Zn star. Okay, and the output of the experiment is 1 if X to the E is congruent to Y mod N. So I managed to find a base X such that you know, X to the E exactly gives me Y. Can anyone already hazard a guess as to what I can do if there is a D with me? If I could compute a D. So I mean the whole assumption will be that, well, at least computing a D will be hard given N and E. But suppose I have D, then what can I do? How can I compute X if I have D? Any thoughts? So this is just to ensure that we're following along, right? So I defined these terms, right? So I gave you an N and E and a D. Okay. I told you that E times D is 1 mod phi n, and phi n is the order of the group Zn star. Okay. Now given all this information, can you tell me if I have a Y and a D along with N and E? So basically anyway I have N and E and Y, right? That is input to the adversary. So the adversary already has N, E and Y. So now if I also have D, can I find this X? Let's try that. So you're saying, well, I have Y, right? And I have N and I have E. Okay, and I have D. Now both sides of what do you want to multiply Y?
The ED is congruent to Y mod 1 mod N.
So ED is congruent to 1 mod phi n.
Oh, mod phi. Y mod.
Very good. So what he said, I mean you don't actually have X, right? So but I think you have the right idea. So what he is saying is that what happens if I compute Y to the D? What happens? So Y to the D is by definition X to the E to the D. So this is X to the ED, and the order of the group is phi n, right? So that means that you will get one sort of mod phi n, right? So this is going to be X mod n, because the order of the group is phi n and E times D is 1 mod phi n, right? So therefore I will recover X. So this will be my trapdoor. And I want to emphasize that this is a very clever idea, and I mean I think it stays just as clever after all these years, right? So just think how surprising it is that you can do this. So you found a problem which is not only hard to invert, but here's a way to invert it using some secret information. Okay, and remember that these things have to really stand the test of time, right? So you don't really know for sure if this problem is going to be hard. For instance, what is the relation of RSA and factoring? This is something to itself think about, right? Yes.
Phi of n is actually dependent on the factor.
Phi of n, good. So one possible answer is that phi of n depends on the factors. Yes. So phi of n actually is going to be p minus 1, q minus 1. So if I have the factors, if I have p and q, I can compute phi of n. If I have phi of n, I can compute d using extended Euclid's algorithm, the way that I already showed you in the previous page. So what did I show? I showed that if factoring is easy, RSA is definitely easy. Yeah, if I can solve the factoring problem, I can split n into pq. I can use p times q, I can use pq to compute p minus 1, q minus 1, which is phi of n. Having computed phi of n, given E, I can compute D such that ED is 1 mod phi n, and given D, I can always invert this function. So let me first just finish writing this. Okay, so the RSA problem is hard relative to this Gen RSA, relative to Gen RSA if for any PPT algorithm A, right, the probability that this experiment outputs 1 is negligible. Okay, and the RSA assumption is that there exists a gen RSA. That means there should be a way to generate these RSA objects, the N and the E in this case. In fact, so what does gen RSA give? Not only N and E but also D. So there should be a way for me to generate this so that the problem is hard. Okay, there exists a gen RSA such that or relative to which the RSA problem is hard.